Hi everyone. Our paper entitled NeuFace, Realistic 3D Neural Face Rendering from Multiview Images, presents a novel 3D face rendering model, namely NeuFace, which learns accurate and physically meaningful underlying 3D representations by neural rendering techniques. It naturally incorporates the neural BRDFs into physically based rendering, capturing sophisticated facial geometry and appearance clues in a collaborative manner. Extensive experiments demonstrate that NeuFace delivers realistic face rendering results, and can be applied to various downstream tasks, such as relighting and virtual meeting. The model also demonstrates a decent generalization ability to common objects. According to photogrammetry, the pioneering studies on capturing face geometry and appearance generally leverage complex active lighting setups, such as light stage, polarized camera, or dynamic blood flow input. An elaborately designed multi-stage workflow is required, typically involving a series of stages, such data acquisition, radiometric calibration, multiview reconstruction, and material estimation. However, the output highly depends on the expertise of the engineers and artists with significant manual efforts, and the multi-step process inevitably brings diverse optimization goals. In this study, we aim at realistic 3D face rendering with more practical settings. To minimize the difficulty of data acquisition, only uncalibrated and unpolarized images from a single shot are needed. Moreover, the images can be collected under unknown illumination. Our goal is to recover high-quality facial geometry and appearance properties with a simple and complete end-to-end workflow. While the task is quite challenging for the following reasons. Firstly, accurately modeling the optical properties of multi-layered facial skin is itself difficult. The unevenly distributed fine-scale oily layers and epidermis reflect the incident lights irregularly, leading to complex view-dependent and spatially varying highlights. Secondly, although several attempts, such as Defrec and RefNerf, introduce physically motivated priors and present physically based 3D neural rendering, delivering substantial gains, the exploited priors are either heuristic or analytic, limited to a small set of real-world materials, incapable of describing human face. Moreover, solving the rendering equation is computationally expensive, since massive Monte Carlo sampling is typically required. To tackle the challenges above, we present a novel face model, namely NeuFace, to recover faithful facial reflectance and geometry from only multi-view images. We follow the physically based rendering paradigm for its potential in learning 3D representations. The proposed NeuFace exploits a spatial MLP and an integrated basis MLP to learn the skin BRDFs and simulates the physically correct light transport by explicitly decomposing it into diffuse albedo, light integral, and BRDFs integral. Compared to the analytic BRDFs, the neural ones allow richer representations for sophisticated material like facial skin. In spite of this superiority, such representations pose challenges to computational cost and data demand during training. To overcome this drawback, we transform the original rendering equation into the derived form, where a low-rank prior is further introduced, which greatly restricts the solution space, facilitating the learning of neural BRDFs. Furthermore, NeuFace utilizes an SDF-based representation, namely ImFace, as the facial geometry prior in forward mapping, so that the facial appearance and geometry field can be synchronously optimized. To auto-calibrate the inconsistent color response and white balance among cameras, a neural photometric calibration module is further introduced to calibrate the radiance. Along with the network architecture, we would like to present more mathematical derivation details of the method. Facial appearance modeling can be formulated as shown, where the equation consists of a diffuse term LD and a specular term LS. The specular term LS is intractable to solve due to the view-dependent characteristic. To accurately capture the spatially varying BRDFs and avoid performing heavy Monte Carlo sampling, we leverage the split integral approximation technique from Unreal Engine, and the specular term can be decomposed into material term and light term, which are solved individually in the subsequent. For the material integral term, we put forward a key assumption that all the facial surface positions of an individual share a similar specular structure, and the spatially varying properties can thus be represented by diverse linear combinations of only a few learnable BRDFs, as formulated in the equation in the third row. The low-rank prior greatly restricts the solution space, thereby diminishing the need for large-scale training observations. It significantly improves the performance of appearance recovering. In our network, an integrated basis MLP is designed to fit B, and the coefficient vector C, x, is predicted by a spatial MLP with x as input. In the light integral term, dh denotes the normal distribution function, We assume that it follows VMF distribution and use spherical harmonics to represent the lighting. According to the properties of spherical harmonics, a close-form solution for the light term can be derived as the last row shows. For the diffuse term in the rendering function, its BRDF's term FD equals alpha x divided by pi, as it is independent of direction. By substituting the spherical harmonic lighting representation into the original formula, we have the equation in the third line. Then, an analytical solution for the diffuse term can be derived by applying the Funk-Heck theorem, as formulated in the last equation. In NeuFace, diffuse albedo alpha x is modeled by a spatial MLP. Finally, the outgoing radiance LO at surface position x along direction omega can be expressed by this equation. In summary, the appearance component of NeuFace is composed of a spatial MLP to learn diffuse albedo, specular intensity, shininess, and linear coefficient C, an integrated basis MLP to learn the BRDF basis B, and the learnable environment light coefficient CLM. We first present the results of novel view synthesis. The compared methods, phi-SG and diffrecon, are also physically based neural rendering methods as ours. However, limited by the inadequate capacity of the analytic BRDFs, they only recover rough facial appearances with obvious artifacts. By contrast, NeuFace achieves realistic face appearances with much richer skin details and high-fidelity highlight. In this video, we demonstrate more results compared with the existing methods. NeuFace even outperforms the geometry-oriented one, namely VolSDF, suggesting that our neural PBR framework benefits not only facial appearances, but also facial shapes. Here, we show the ablation study results by replacing our neural BRDF with Disney BRDFs. The first and third row results demonstrate that the proposed neural BRDF's module can capture high-fidelity reflections of facial skin, such as the reflectance around grazing angles, while such light transport cannot be well modeled by Disney BRDFs. We also compare SH lighting with CubeMap. As the second and third rows show, in the under-constrained settings, CubeMap fails to accurately relight faces under new environment maps. In contrast, NeuFace can well adapt to arbitrary lighting conditions. NeuFace also demonstrates a decent generalization ability to common objects. It achieves more impressive reconstruction and factorization qualities than the compared diffrecon method. Impressive results have been achieved even on complex scene, demonstrating the robustness and effectiveness of our approach. Thanks for your attention. For more information about the NeuFace model and evaluations, please refer to our paper and code. Welcome to our GitHub repo.